Hello, dear learners. Once more, welcome to our session. We're going to explain to you how to determine the limit of a function. Presentation is done by Professor Janko. Please, your advice to like, comment, and share this video, and why not subscribe to this YouTube channel. For more information, this is my email address on the screen. You can email me if you want a one-on-one personalized tutorial online session. So we are going to talk about limits all through our conversation. We'll begin by defining what a limit of a function at a given point is, and we are going to go through examples. To define the limit of a function, consider the following definition. We have that the function f of x is said to have limit L as x approaches some values a if as x gets really close to a, f of x gets as close as we want to L. And the notation is given by the following. The limit as x goes to a of f of x is equals to L. This is the notation. To understand precisely how this actually looks like, we have a function here, we have our x-axis, here we have our y-axis. We try and get towards the point A from the left-hand side. We move from the left towards A, and the value of our function at this point is close to L. If we move from the right of our graph on the x-axis from the right, we move towards A. What happens? The value of the function at that point is goes towards L. That is the graphical representation of the meaning of the limit as x goes to a of f of x equals to L. So the limit from the right, from the left, is equal to the limit from the right for us to have the existence of a limit at that point. To basically explain to you how this looks like, let's have a look at small examples. Here we want to find the limit of three types of functions: constant function, linear function, and rational function. The first function is a constant function that we're going to evaluate the limit here. The first example says, find the limit of the function 7 when x goes to 3. Second example, the limit as x goes to 1 of x plus 5, which is a linear function, x plus 5. We have to evaluate the limit as x goes to 2 of our function x squared divided minus 4 divided by x minus 2. We're going to go step by step. We'll begin with the first function, which is the constant function. So this implies that we can do it using a table of values to see the behavior of the function. So you can decide to actually draw a number line here and put your values for your x values. Let's say here we have our minus 3 here. So we're looking for values going towards the value x here, which equals to 3. So we're looking for values going towards 3 from the left of our number line and going towards 3 from the right of our number line. This actually helps you visualize the type of values you put in on your table. So from the left, we have, for instance, x equals to 2. So at x equals to 2, the value of our function is a constant function, 7. So the value of the function at x equals to 2 is 7 from the definition of the function. So here, our f of x equals to 7. This is the function here we have here. So at any point, 2.2 we have 7, 2.4 we have 7, up to 3 we have 7 as well. From the right, we choose maybe, for instance, 4, and we go gradually up to 3. 3.8 we have 7, 3.6 up to 3 we still have 7. So as a conclusion, we're going to see the limit as x goes to 3 of 7 is equals to 7. Graphically, how do we represent this? We have our x-axis and we have our y-axis here. Here is 0. Let's say here is 3 and here is 7. We have a horizontal line going through 7, right? a horizontal line going through 7. So no matter where you move from to 3, you will still have the same value of the function. So we said if you have 2 here, the value of the function at the point 2 is 2. If you have 2.4, the value of the function is 7. If you move from 4 towards 3, the value of the function is 7. Even up to the point 3 itself, we have 7. So the limit as s goes to 3 of 7 is 7. That is how we evaluate the limit of a function, of a constant function. Now, let's look at a linear function. We have the limit as s goes to minus 1 of x minus 5. Once more, you can draw your number line so that you can have a vision of the numbers you will put on your table. We have here 0, we have here minus 1, and here we have 1, and here we have, let's say, minus 2. So we move to minus 1 from the left. These are values here. So we check from minus 2 here up to minus 1. What do? You say when x equals to minus 2, wherever you see x in your f of x here, you replace it by minus 2. So you're going to have minus 2 minus 5. The answer is minus 7. When x equals to minus 1.8, remember we're going towards minus 1. So we'll x equals to minus 1.8. We replace x by minus 1.8 and the answer is minus 6.8. So you go gradually and you do the same process until you get to minus 1.0. You place wherever you have x here, play by minus 1 and the answer is minus 6. You see from the left, the value of the function at the point minus 1 is minus 6. So from the right, we check values here, maybe from 0 up to 1. So you have 0 here, you put 0 wherever you have x on the function f of x, you're going to have 0 minus 5, and the answer is minus 5. You go to minus 0.2, you place by x by minus 0.2, you're going to have minus 0.2 minus 5, and the answer is minus 5.2. You do likewise until you get to minus 1, you play by minus 1 here, x by minus 1, to obtain minus 6. So from the left or from the right, what happens? The value of the function is equals to minus 6. And graphically, this is what we're going to have. Let's say 1 here. Let's say 2 here. Here we have our 0. Here we have our minus 1. Here we have our minus 2. Let's have our minus 2 here, minus 4, and minus 6. Okay? So this implies we're going to have a minus 7 somewhere here. So at x equals to minus 2, we have our minus 7 here. When x equals to minus 1, we have, let's say, minus 7, minus 6. And when x equals to 0, we have a minus 5 here. So you connect the points. Oops, disappeared. Minus 6 here, minus 5 here, and here minus 7. You can connect. You're going to have a straight line graph. And that is how your function will look like. So alternatively, if you're asked to determine the limit of a linear function, what you can do, if you don't want to go ahead and sketch the graph or have table of values for a linear function, the easiest way to evaluate this is to do the following. You write the limit as s goes to minus 1 of x minus 5. Wherever you see x, you place by minus 1. So you have minus 1 minus 5, and the answer is equals to minus 6. This is how you evaluate the limit of a linear function. Wherever you have x, just replace by minus 1 or by minus by the point at which you're evaluating the limit, and you simplify to obtain the value of the limit of a function at that given point. That is how we evaluate the limit of a linear function. Let's have a rational function. In this case, you're going to evaluate the limit as s goes to 2 of x squared minus 4 divided by x minus 2. Once more, to be able to know the type of values you have to put in your table, you can draw again your number line. Where you have 0, you represent your 2 here. Let's say here you have your 4. So you're going to move to 2 choose values from the left going to 2 and also choose values from the right going towards 2. Before we move on, there's something I'd like to point out. Have you noticed that at x equals to 2, this function will be undefined simply because on the denominator, you're going to have 2 minus 2, and 2 minus 2 is 0. Division by 0 is not allowed in mathematics. So that's why the function is undefined. So if you choose your value, you will not choose 2 because the function is undefined. You're going to choose values close to 2. That's why here we've decided to start with 1. When x equals to 1, wherever you have x here, you place by 1 and substitute for x equals to 1 here. At this point, you're going to have 3. When x equals to 1.2, you have 3.2. You go close to, you see what we've done here. At some point, we've decided to reduce the intervals. So from 1.8 to 1.85, simply because we can't get to 2, because at the point 2, the function is undefined. And what have you noticed? The value of the function goes gradually up to what point? 3.94. And if you run up here, you are going to have 4. Likewise, from the right, if you decide to use 3, you put 3 into the function, you're going to have 5. You put 2.8 into the function, you have 4.8. You go gradually towards 2 from the right, up to 2.05, you're going to have 4.04. And you see that it goes towards what? If you run it up, it goes towards 4. And that makes sense simply because if we try and simplify our function here, what can we observe? The numerator more or less looks like the difference of 2 squares. If you have, let f of x here be equal to x squared minus 4 over x minus 2. This is the same as x minus 2 times x, the difference of 2 squares, because 4 is 2 squared, right? So you're going to have x minus 2 times x plus 2 divided by x plus minus 2, right? So this cancels. Our f of x will now be equals to x plus 2. And the value of the function at the point 2 is equals to 2 plus 2, and the value is what? 4. So because the tendency of the function when it goes, remember the limit is the value that we need to have from the left and from the right of that point, precisely of the point 2. So the limit as x goes to 2 of x squared divided by 4, x minus 2 is 4 from this explanation, okay? Now, if you want to represent this graphically, what can we notice? We notice that if you have our function here, we have values of x here. Here we have 0. Here we have our x. As you remember, we want to move towards 2. So we can have our 1 here, our 2 here, and our 3 here. So the values of our function ranges from what? It ranges from 3 to 5. So let's have our 2 here, our 4 here. Let's have 6 here. So when x equals to 1, the value of the function is 3. When x equals to 2, it is a whole, because at the point 2, the function is undefined. So it's a whole. We call it a whole because the function is undefined at the point 2, but when we simplify it, we get 4. That is why we put our 4 here as a whole. And when x equals to 3, we have 5 somewhere here. So we draw our straight line. At the whole, we have what happens here, a break on the straight line. So this is how our function looks like graphically when we represent it graphically. So this is how we look at the limit of a rational function at this point. So we first begin by simplifying the function and evaluating the limit of the simplified version of the function. We can have our table of values and observe the behavior of the function when it goes towards that point. For more examples, we can look at this graphically. Here we want to evaluate the limit of this function when it goes towards 0. Look at what happens here. When we go towards 0 from the right, what happens? Let me get the pen. When we go towards 0 from the right here, the value of the function goes towards 2. But when we get towards 0 from the left, the value of our function goes towards what? -2 here. So because the limit from the right is different from the limit from the left, at this point here, we say that the limit does not exist because from the limit from the left and from the right are different values. And if you look at this function here, the limit from the right and from the left are identical. If you move to 0 here from the right, what happens? The value of our function tends towards what? 2. If you move from the right, from the left towards 0, the value of our function moves towards 2. So because the value of the function from the right and from the left is identical, it goes towards 2, therefore the limit exists. So one requirement for existence of limit is that limit from the left and from the right must be identical. So what did we study? We have studied the limits. We've given a definition, the notation. We've evaluated how to find the value of the limit of a constant function, the limit of a linear function, the limit of a rational function. And we've observed some more examples whereby we could examine the limit graphically. Thank you for listening up to this point and for watching up to this point. We see you in the next video. Thanks once more. See you in the next video.